All right, guys, let's find our seats so we can get started. You don't want to be front row, Dima? All right, we're going to get started now. So welcome, friends and family, to our Nanoscience Lab 2025 final presentations here at the California Nanosystems Institute at UCLA. My name is Dr. Shailene Tanimoto, and I'm the Education Manager here at CNSI, and I've been with your students for the last 5 days watching them grow and learn all these wonderful things about nanoscience, and so we're very excited today to show you all that they've learned. So first, I'd like to welcome you all to UCLA. UCLA was founded in 1919 and is the second oldest school in the UC system. Our UCLA offers over 330 undergraduate and graduate degree programs with over 33,000 undergraduate students. 7% are international students, 29% are first-generation undergraduates, and about 30% of undergraduates are in the life and physical sciences. And we're here today at the California Nanosystems Institute, or the CNSI. And so the CNSI is one of Governor Gray Davis's Institutes for Science Innovation, located here at UCLA. It was originally established in the year 2000 as an engine for innovation based on the belief that the defining technologies of the 21st century will arise from understanding and constructing functional nanosystems through controlled integration of nanoscale components. And so our mission is to be a world-leading nexus of research, education, and translational activities by engaging in scientific discovery that fuels innovation and impacts society. And so this is our education team. And so the CNSI is technically a department at UCLA, but we are not a degree-granting department. But instead, we're an interdisciplinary hub for research, technology, education, and entrepreneurship. So our education team is led by Professor Sarah Tolbert, who's a professor in the Department of Chemistry and Biochemistry and Material Science Engineering. Our education director is Dr. Rita Blake, here in the front row. I am your education manager, Dr. Shailene Tanimoto, and our education program coordinator is Dr. Elaine Morita. And we run various programs, including professional development workshops for K through 12 teachers. We have a Nanovation competition for 6th through 12th grade students, which combines nanoscience and entrepreneurship. We host several public outreach events. And what you all are here for are our summer session programs for high school students. And so our Nanoscience Lab course is a one-week summer program for rising sophomore to graduating senior high school students from around the world. We have 40 students enrolled this summer in our college-level science course that focuses on nanoscience and science communication. And so we have these learning objectives for the students that we've worked on throughout the week, including these skills in science, so particularly about nanoscience here at the Nanosystems Institute, but also being a scientist. And then we also know that maybe not all of your students will go on to be scientists, so we also have these skills in life that we have them working on. And so these are skills that are important for scientists, but also just important for everyday people. So this includes the growth mindset, which is the belief a person has that they can learn more or be good at anything if they work hard and persevere. And let me tell you, your kids worked really hard and persevered through some really tough assignments and challenges this week. We're going to talk about our homework that they had this week, but in their homework assignment, which they're going to be presenting on today, they had to combine a lot of these skills, including critical thinking, communication, collaboration, teamwork, empathy, creativity, curiosity, problem solving, and reflection and introspection. And so you can see from our course schedule that they had a jam-packed 5 days where they performed nanoscience experiments every morning, They heard some guest lectures from UCLA faculty and staff, and then they rotated through science-themed activities that were relevant to the experiments that they performed in the morning. And so here are some pictures that I took throughout the course. I don't know if you guys knew that I was taking pictures of you, but here are some pictures that we had of our morning experiments. You can see we were out in the lobby, and they were performing these experiments. I have some pictures here of our amazing guest lecturers that came and gave talks. And then lastly, some of our afternoon activities where they got to go to the chemistry department, down to our clean room, and some of the various technology centers that we have here in the CNSI. So a lot of amazing people helped to make this happen. And so before we start the presentations, we just like to take a moment to thank some of these people. So first are our Nanoscience Lab instructors. We had 25 instructors over the course of 5 days who helped teach your students about nanoscience and what it means to be a scientist. These instructors come from various departments, including physics and astronomy, chemistry and biochemistry, material science and engineering, bioengineering, chemical and biomolecular engineering, and all of these students do nanoscience research. And so I'd like to take a moment to thank all of them. Then we had our residential assistants, and so we had 20 students who were living in the dorms and 20 students who were commuters. But our RAs are amazing human beings, and they lived with 20 teenagers for a week. So yeah, congratulations on surviving that. But more than that, they hosted office hours in the evening, both for our residential and our commuter students to help them with their really challenging homework assignments. So we really want to thank them. And then we had our amazing guest lecturers. So we had 4 amazing guest lecturers who talked to your students about their journey from high school to where they are now and how they apply nanoscience in their current research. So we had Dr. Adam Stieg. He's the Associate Director of our CNSI Technology Centers. Professor Ben Schwartz, who's in the Department of Chemistry and Biochemistry. Dr. Paloma Castellera Costa in the Department of Electrical and Computer Engineering, and Professor Dino DiCarlo in the Department of Bioengineering. So we just wanted to thank them for taking the time to talk to your students. All right, and lastly, we have our CNSI, our Technology Center staff and our CNSI staff. And so, like I said, your students got to tour our various technology centers at the CNSI. We had lunch provided for the students throughout the week. And then we are live streaming currently. And so we have all of these people to thank for making all of this happen for us this week. So thank you. All right, so now's the time for our main event, which are our final presentations. So again, our main goals for this class are to expose your students to advanced topics in nanoscience, and we want to develop their life skills and science communication skills. And so to this end, the students completed a homework assignment each night in which they had to draw a picture that explains the essence of the experiment that they learned that day without making it a literal figure. So it should be something that is understandable to someone who is unfamiliar with nanoscience or the topic that they learned about. And again, the goal is to capture the essence of the nanoscience concept in an original pictorial analogy. So you'd want to relate this nanoscience concept to an everyday scene, idea, or phenomenon so that someone without any science knowledge could understand that concept. So if that sounds really hard, it's because it is. And I think that even some of our graduate student instructors would struggle to do this. And so it's a really difficult challenge that we pose to your students. And let me tell you, they produce some really amazing things that you're gonna see today. And so we've collected some of the best homework drawings from this week, and groups of 4 will present on these pictures, which was drawn by one of their classmates. So The students will have 5 minutes to introduce themselves, provide you the context of the experiment that we performed in class, walk you through what the drawing literally shows, and then discuss the scientific concepts represented in the image. And then they'll also discuss the limitations of the analogy or the science concepts that were not fully captured in the image. And so all analogies will have limitations because they are all imperfect representations of the complex scientific topics. And so we just want to remind our students to be kind while providing critiques of the artwork and what concepts aren't covered. And when we talk about how the drawing might be improved to better represent a concept. All right, so this is our presentation schedule. And then they will have 5 minutes to present on their drawing, and then we'll have 5 minutes of questions from the audience. And so, I'm looking at all my parents and family members. We highly encourage you to ask questions so that you can better understand what your students learned this week, but also because we have some very bright scientists in this room, including Dr. Rita Blake. When Professor Tolbert gets here, she will also have lots of questions. And then we have our graduate student instructors as well. So they will ask very challenging questions. And so we encourage you to ask your questions so that your students can explain to you what they learned. So we will have the first 5 groups present. We'll take a 10-minute break, and then we'll resume for the final 5 groups. All right, so group 1, come on up.
I'm Elon Shapiro, and I'm from LA.
I'm Sarah, and I'm from LA.
I'm Will, and I'm from China.
I'm Izarelli, and I'm from the Central Valley.
So first, I'm going to talk a little bit about the actual experiment we did in class. So the goal was we were measuring nanoscale spacings on a diffraction grating. So we had this little thing that was plastic, but it had these nanoscale gratings on it. And what we were doing was we held it at different lengths, at different heights above a piece of paper, 4 centimeters, 8 centimeters, and 12 centimeters. And we shined a laser through it. And what we saw was the light from the laser was diffracted through the gratings, and there was different dots on the paper that were evenly spaced, and we measured the distance between those dots. So we did that we couldn't see the nanoscale gratings, but by doing that, we were able to measure and see that, like, we knew they were there, even though we couldn't see them because they were so small. And then after that, we also imprinted the grating onto a silicon-based polymer and actually a piece of chocolate, and the light was still able to diffract off of those things that we imprinted them off of, and we could eat the chocolate.
So what we see is 2 banks. We see a bank on the top, and it shows 2 people. The person on the top, it says 1 cent times 10,000, which equals $100. And the other person on the bottom, he has $100. So I think the top person, he's bringing in the $100, and the other person's taking it out. And then the side, it shows the economy, and it's going down. And then the top, it says it's closed. On the bottom bank, we see 2 persons. The top person, he has a little thing that says 1 cent times 10,000, which equals $100, and he's bringing it in the bank. And the bottom person, he has $100 too, and he's bringing it in the bank too, which makes $200. And then the side, it says open, and the bottom, it has a little chart with says economy, and it shows pointing up.
Okay, so I'm going to talk about like how the scientific concepts we learned that day relate to it. So one of them is indirect measurement. So for this, it's judging the economy, which is kind of hard to measure in full, based off of the performance of banks. So it's saying that if a bank is doing well, like the one on the bottom, it likely means that the economy is going up. So indirect measurements are pretty much when you measure something that you can. It's like a related value to find what the exact measurement of something that you can't measure is. So like for the one that we did in the experiment, we were able to find like the distance between the different gratings by measuring the distance between the dots and then using some trig to find exactly what the grading was between the two small ones. And this is similar because he's not able to, it's like hard to measure an economy, so you're basing it off of a known value of a bank, which is related. And then you can also see with the arrows how on the top, one of them is pointing in with the guy with the hat, and one of them is coming out. And then on the bottom, they're both going in. So this is representative of constructive and destructive interference between waves. So one of the things with light waves, the reason that it has those diffraction patterns is because of the interaction between the waves. So constructive waves are when the peaks of waves are aligned, so in the top part of the wave for both waves. So that looks like the bottom because both of them are aligned. And destructive interference is when the peaks are aligned with troughs of a different wave. And the thing with constructive and destructive is that if it's constructive and both of them have like the peaks aligned, the wave gets bigger. And if the peaks are aligned with the troughs, then they cancel out. So here they're canceling out on the top because while he's putting money in, the other guy's taking money out, so it ends up with 0. And on the bottom, they're working together, or like non-intentionally, but they're both adding to the bank. They're doing the same thing. So the bank is like, it makes money and it's positive. And then also there's a concept of measuring like the nanoscale and like how nanos add up, like how they're relevant on the human scale. So there's the 1 cent times 10,000, and it's equal to $100. So that's kind of representative of how things that are super small, like these nanoparticles that we've been talking about, can add up and be relevant to human scale because they like things that are human scale are made of small nanoparticles.
Yeah, I think one limitation of this image is that the content of atomic force microscope AFM is not included in the image. Besides, and the symbol of cent in the image is often misinterpreted as the number 14. It can be misunderstanding in some extent. Yeah, that's all. I'm finished. Yeah.
No, he's finished.
Oh, he is finished.
Yeah.
Okay, great.
Yeah, 5 minutes questions, please. All right, questions from the audience, please. Great.
Does shining the laser on the chocolate make it taste better?
Great question.
Not noticeably.
But to make it, we first like melted chocolate and then we froze it with the pattern on. And cold chocolate actually tastes like really good. So it kind of improved it by being cold. So I don't know, maybe it did.
So one concept that you guys briefly mentioned is diffraction. But for those of us in the audience who maybe don't know what diffraction is, can you guys please describe it and how it related to the phenomenon you saw in the experiment?
Okay, so when there's like something that is like a light wave is like kind of coming in, right? And then these little grates, instead of allowing it to go straight, it kind of like bends them because of the holes. So from that, the light waves, instead of just being like a straight beam of light, they're spread out. And because there's multiple of these gratings, they spread out and they're diffracted. But then other light waves from other holes are also diffracted, so there's some canceling out, and then there's some where it creates the peaks where they're aligned, and it creates like the lasers that you can see on the dot.
Okay, I have the really hard question. You guys talked about light waves. And so the concept of constructive and destructive interference is well described here. But it's like individual point people. And I'm going to ask this to everybody, these kinds of questions. Could you imagine a way to convey any of the properties of waves in an analogy like this?
Like with the banks, this analogy specifically, or this topic?
Either. I'll give you any way you want to finesse. By the way, when you get a hard question, a good way to answer it is to answer an ever so slightly different question if you can't quite answer the question that you're asked. That's a common tactic that everybody employs. But you may interpret my question any way you want.
But once you answer it, please answer into the mic so that we can be sure to pick it up.
Okay, we have an idea. So maybe there could be something like, there could be holes and maybe like interactions between like arrows and those holes. Like, so maybe you could see the diffraction and like how it moves around objects. And then also maybe you could have like different sizes and like different results from those sizes. So maybe you could have like a longer arrow indicating like a longer wavelength. And then somehow that could be indicative of like lower energy or something.
Yeah, that could do. Also something to do with overlap, because the whole idea of constructive and destructive interference is that you have light waves at the same time in the same place with different phases. So that sort of same time and same place is a concept that one could think about. Good job.
All right. Thank you. And before we move on, who is our artist? All right. Please state your name and if they accurately described what you were going for here.
My name is Jackie. I think they did a pretty good job describing the picture.
Thank you.
Sarah, did you want to say anything before we go?
Okay, Professor Sarah Tovich is here, so she's going to add on to our welcome remarks.
Hey. Hi, so first let me apologize for not being here at the very start. I had another meeting and they all just overlap. But it's a pleasure to be here. I've gotten to talk to your students a few times during this week. I am a professor in the Department of Chemistry and Biochemistry and Material Science and Engineering. And I am the official instructor of this class, even though your amazing graduate student TAs and Shailene and Rita were the people who were there for sort of every minute with your students. And I just want to say that this exercise of creating pictures out of science is one of the things that scientists do all the time in a goal of conveying knowledge to the general public. And I will just say that in a time when science in general is under attack, we all need to learn to communicate really complicated concepts in a simple way so that everybody can understand them, appreciate them, and realize that things like funding science are actually a very good thing to do with your tax dollars. Not to get political, but science is important, at least to us, and hopefully if you send your kids here, probably to you as well. And so what I will say is conveying science to other scientists is astronomically easier than doing this, because to come up with a way to convey a complicated idea in a simple form means you really need to understand everything about that complicated idea enough to the point where you can simplify it down. And so we are giving your students an extra hard job, not an extra easy job, by having them try to make these general analogies. And then I will just end by reiterating that this is supposed to be a community experience, and we really want you to all ask questions. And if you don't ask questions, I will ask questions. And I bet your questions will be easier than my questions. Good to have some easy and some hard questions, but it's much more fun when everybody's involved. So please do try to ask questions and enjoy all the talks.
All right, thank you. All right, with that, let's bring up group 2. So we've got this guy, we've got 2 handhelds. I remember you guys can use the laser pointer to help the audience follow along, okay?
Hello, I'm Victor.
I'm Hudson. I'm from Huntington Beach.
I'm John, and I'm from Illinois.
I'm Tiana. I'm from China.
So what we did on Tuesday was we made solar cells, which are about like 1.5 inches wide, and we used conductive gas, titanium dioxide, which is an ingredient that's found in white paint, raspberry juices dye, and then graphite and iodine. So what happened was photons from the sunlight went and got absorbed by the dye, and then it shot off an electron, which traveled through the conductive gas and was able to produce power.
So starting from the left, we have a house that has meat hanging from it because that's what normal people do. And this is attracting wolves. And at the bottom, there's a house with carrots on it, and it's attracting rabbits. And so these little people, they're coming out from the house, and they're going out of the gate and going around and back to the entrance at the bottom over there. And then they move on to a hotel. And then from the hotel, they go to a realtor and then a bank and then back to the houses.
Okay, so I'm gonna go through the analogy. So first, starting from the monsters at the top, we think that the monster represent the sunlight because, so first of all, they're very energetic. And then the houses and the meat, we think that the meat is actually the dye because theoretically, the dye should absorb the energy from the sunlight. And then you can see how the monster and the meat, they're paired. And then we think the house, that's a TiO2 because in the real solar cell, the TiO2 are attached to the dye, and then the TiO2 has the large surface area, and then we think the house is sort of demonstrated like the large surface area. And then we can see how the electrons, which are the people, they are excited because they're scared by the monsters, and then they are traveling, and then they're exiting the cell, and then through the electrode, and then going down there, and then you can see, and then it's you can see how the electrons is like doing work, maybe like working out, and then yeah.
And then wait, afterwards, the electrons, they go back to the electrode, which is the guy pointing in the welcome sign. So that's like what's conducting, that's like what's pointing the way for electrons to go. And then the electrons enter the hotel, which we think is the battery or the power source where they get stored in there. Oh wait, thank you. So yeah, the electrons would get stored in the hotel, and then they would exit out, go to the realtor, which is, the realtor is, the iodine. So the iodine, so the dye on the meat, right? It's supposed to lose electrons. So something has to replenish the electrons to the dye to make sure that the cell can keep working. So the realtor gets people, probably gives people cheap deals, and so they want to go back to the houses. You see that for sale sign, yeah. So the realtor is what gets people going back. And then to the left of the realtor is the bank, where we have people borrowing money, which serves as a catalyst or something that speeds up the reaction, speeds up the electrons going back to the houses. And they do that through the money, which is they can just borrow the money so that it just makes the process easier so that they can go back to the house. And yeah.
Okay, so we're gonna go quickly through the limitations of the analogy. So first of all, we can see like the electrons that are coming out of the house, which is the TiO2, but actually they're coming out of the dye. It's like the dye releases the electrons, so it's not precise.
Another thing we had was that the position of the hotel is a little confusing because in reality, the storage won't like always resupply the electrons back to the solar cell, so it doesn't really make that much sense.
Another limitation is that because it's a cyclical nature, there isn't really an obvious beginning to the cell.
All right. Questions from our audience, please. I'm not looking that way at Dr. Rita Blake, who has her hand raised.
What does the house with the carrots represent? And why are they so happy?
Okay, I'm sorry.
Happy people don't put carrots on their houses.
So I think why they're happy, you should ask the artists first. And then I think that because there's a house with the carrots and the rabbit, so we think that actually that represents like the difference, like how the difference of voltage and current works. So you can see the rabbit is not as scary as the monsters, and then you'll see like I think that represent maybe smaller voltage, and then you can see the carrots. It's like you got only maybe 3 to 4 carrots on a house, but you get like loads of meats there, and then we think that represents like a smaller current because the carrots may be also the electrons, and then you can the smaller current means that you got less electrons passing by the maybe wire or circuit or anything. Yeah.
To add on to that, we were saying that the rabbit is like a smaller frequency of light than the monster, so it has less energy, which is why it's lower voltage.
Okay, so I want to just follow up on this. So you said that the monsters are scary, and so the people run out of the house, and so the people are electrons, and they're excited. So given that description, can you talk a little bit more about the carrot house?
Maybe they're allergic.
Well,
So, the carrots are like the dye for the lower frequency of light. The rabbit's the lower frequency of light. It carries less energy, which is why people are less scared of the rabbit than they are the dogs. So it would be like instead of the solar cell having red dye, it had a lower frequency. So,
but I think there's a way simpler thing, which
Okay.
is just in the solar cell, what's the first thing that happens?
light goes through.
Light is absorbed, and it creates what?
Voltage and current.
Well,
It
so-
like excites electrons.
It creates excited electrons. And so the people running away from the wolves are excited electrons.
Yeah.
After those electrons go through and they do work, and then they go through the iodine shuttle, and then they come back. What state are those people or those electrons in?
They're not excited.
They're not excited. So what is the carrot house?
It might get people excited because it's the only safe house, maybe? I mean, it's ground state.
Yeah.
Oh.
It's just ground state people. Apparently carrots are so boring, they're just ground state people. Carrots are in the ground.
All right. Any last question? All right. Thank you, Group 2. Okay, and our artist. Okay. Please state your name and if they captured all the things that you wanted them to.
I'm Carter, and yeah, they basically said everything that I was trying to convey, and someone even caught the treadmill, so.
Are carrots supposed to be in the ground?
No, the carrots were supposed to represent, like, theoretically, if we used a different dye, it would attract a different kind of animal or a different kind of light, so in this case, it would be rabbits instead of the wolves.
I guess the happy person then is they're still excited, right? But not like so excited that they're running away.
Or maybe they are. Maybe it's an alarm, like a megaphone.
All right, group 3.
Okay, while group 3 comes up, I just want to remind people of the language thing we talked about. No analogy can possibly ever be perfect. So you're not trying to say this is what was left out or this is what was done wrong. These are just the limits of this analogy and what is the real physics that this analogy couldn't capture. So please try to think about how you discuss this, because it's intrinsic to any everyday analogy that it will only capture part of the real science of the system. Okay.
Hello everyone, my name is Bria Yang. I'm a rising junior and I'm from Illinois.
Hello, my name is Alicia Tai. I'm also a rising junior and I'm from Ontario.
I'm Austin. I'm also a rising junior. I'm from China.
Hello everyone, I'm Ray and I'm a rising senior and I'm from Taiwan.
For our experience, we wanted to know like how much glucose, which is sugar, is in the drinks, just like how sweet it is. But instead of tasting, we use a sensor which can make something you can observe to something you can observe. It made with beams with special solution that can change color to pink when there's glucose. Depending on the result, the sensor must be complete. That each part of the beads and the special solution are necessary or it won't work. We put the sensor in glucose solution with different concentration, and then we put many drinks so we can compare how strong the color is and got how much sugar it contains. We also check how this works in different environments. Luckily, it worked perfectly fine, but without the beams, the solution itself cannot work in the base environment.
So we're gonna analyze the picture for scientific concepts of the experiment. So in the graph, we can see a guy named John is trying to plant something. And on the right-hand side, there are two ways to plant, plow and not plow. The upper one is plow, which is faster, and the lower one is not plow, which is slower. On the left-hand side, there's the timeline of planting there, from putting the seeds in the soil till the plants are fully grown. And next to the fully grown plants, there's a bunch of different characteristics of plants, such as their color and their heights. And at last, in the middle part of the graph, John gets that his plant had grown into medium fertile. So jump into the scientific concept. First, we interpret the options of plowing as the enzyme, since enzymes are basically proteins that act as the catalyst that helps some components to accelerate their process in a biological way. The points we discovered that the acceleration is the options to plow, and the tools, which is the plow, act as the protein.
All right, now on the left side, we see that John is trying to grow some sort of crop on his field, and he plants seeds to do it. This is actually an analogy for a sensor, which is a device that is used to measure some sort of information, process it, and like translate it to something that is easier for us to understand. Now, John is trying to test how fertile his field is. So in this case, he's testing the field, but the field is also the sensor. So here, first, how a sensor works is it has 3 steps. It receives a signal, and then it processes it, which is called transduction, and then it gives a response. So in this analogy, the signal is the seeds. He's planting the seeds, and then the field is supposed to like process the seeds, which here it says several months later, so that's transduction, the second part. And then the last part is when the crop grows out, and that's the response of how fertile his field is. But to understand this response, we have to compare it to something, right? Like when you take, wait, never mind. This, in scientific terms, is called the calibration curve, and it's a device that's used to compare test results. It's like a standard for comparing test results. So here we see that the standard field, it would be like black and low if the field was infertile, and then if it was fertile, it would be golden tall. And he compares it, and he sees that his field is medium fertile. And it's also a colorimetric sensor because it gives color.
Okay, also another analogy that we also saw was that the field is wrapped in a fence which acts as the nanoporous bead, which usually in like experiments it like helps protect the enzyme and keeps the reaction stable, and in this case it would like protect the crops and like allow for better growth. And then moving on to the limitations, one of the limitations that we saw was that the encapsulation may not be noticed in all of the fields, which would affect the way how like if they actually grew it, affect the way the plants are growing. And okay, yeah, okay. And then I had one more limitation, which was that the image includes like a sensor, but it's not super clear to see which part is a sensor, as like there may be different interpretations, as the signal may start from the field or it would start from one of the tools that they used.
Okay, questions from the audience? You can ask a question.
Sure. Is the plant the sensor? Is that accurate? Like, from what I'm understanding, is the plant like the sensor for how fertile the field is?
No, the field is the sensor, right?
It's all an interpretation, so
'Cause-
if that's your
okay.
interpretation, just
Yeah,
elaborate on.
we think that the field is the sensor because you need to give like some sort of like information in a sensor, which would be the seeds, and then it would like grow out to be a crop, and that would be like the response.
Actually, I have my points that like the flow and not flow is like the signal because it's like what we want to observe. Like it's like the start of the sensor. Oh, okay.
Yeah, and you guys are four different people. You don't actually have to agree.
Yeah, and the thing about these images is that there can be multiple interpretations, right? So you guys can have different opinions, and it's fine.
So my question relates to your interpretation of the encapsulation. So I think you guys said that the field is like fenced off, so that would be the encapsulation. But I think there's a difference between the way encapsulation is working here and the way encapsulation is working in the experiment if the plow is the enzyme. So could you maybe think about what that difference might be?
So for the encapsulation part, we think that the fence is not very clear because it's only 3 sides, so it's not really an encapsulation. Yeah.
So here, let me pose it to you in a different way. So, so what part of this system did you define as the enzyme?
So the acceleration part, which is faster, the plowing process.
The plow, right?
Yeah.
So what is the encapsulation primarily meant to protect in the experiment? Why did you encapsulate? What was the point of encapsulating the enzyme? What can happen to an enzyme over time and under different harsher conditions? And what happens if it changes structure?
They don't.
Then it doesn't function anymore, right? So then what would be the difference between what is being encapsulated there versus what was being encapsulated within the experiment? So if the point of in the experiment was that you needed to encapsulate the enzyme, how would this be different than that?
The plow doesn't really change, like it's this, right? Yeah.
You can go for it.
It wouldn't change like over time, like it's.
I think the simple idea is you have an encapsulant, you have an enzyme, and then you have a substrate. and then you have then you have something that transduces that to get a colorimetric output. And so those are the pieces that you should try to map onto this field, this plowing, and this growing plant.
So you're saying like the encapsulation isn't encapsulating the enzyme itself?
Yeah, in this case, if the plowing is what is accelerating it, the fence is not, and by the way, 3 sides, you can't draw 4 sides unless you're a way better artist than I am. So we will give all artists benefits of the doubt for leaving things out for clarity. But there is an encapsulation, but it doesn't quite map on to the encapsulation in the real experiment. And that's just a limit of this analogy, which is totally fine.
All right. I think we are out of time. Okay, thank you, Group 3. All right, and who is our artist?
Okay, state your name and
Hi, I'm Crucis. Actually, I'm a little bit sorry. So the fence, I just drew it without thinking. So it doesn't symbolize anything. But if you if you just want to say that it symbolizes something, I think it's okay. So actually, John's purpose is to examine if the field is fertile, not plant is fertile, and consider the question that which is the sensor. I mean, actually, the comparing system is the sensor. I'm actually showing how the sensor works. Like it compares to John's field to the standard field and to measure the color. So we cannot directly see how fertile the soil is, but by observing the plants that grew on this land, and we eventually know how fertile this soil is. But I think Group 3 described in a relatively precise way, so there's not a big problem. Yeah.
Thank you. All right, Group 4.
Hi, so I'm Rayhan. Well, yeah.
I'm Carter.
I'm Crucis.
And I'm Rodak.
Okay, so starting off, this was yesterday's experiment. Basically, we did photolithography, which is using light to imprint a pattern onto a specific material. In the case of yesterday, we were basically trying to make a circuit. So we had a substrate, which was a yellow piece of plastic that had a layer of copper and then a photoresist, which is something that reacts to light. And then we put a mask on it that had a certain pattern. We exposed it to UV light, and the parts that were exposed were scratched off by the developer and etched off. The copper was later etched off, and then finally we stripped it using nail polish remover to basically remove the layer of photoresist, and we were left with a circuit in a specific pattern that matched that of the mask. And this process is used in things like semiconductor manufacturing by companies like ASML, and basically they're trying to make these very, very small circuits.
Okay, so literally in the drawing, we can see 3 rows on the diagram. So the first row, it has 3 sets of blueprints. There's a blueprint large, which has like a 30 feet like width or like walking distance. And here the medium one has like 10 feet of walking distance, and the smallest one has the most, like, I would suppose these are counters or like shelves, and it has a 5 feet walking distance between each. So in the middle row, we show this man walking along each of these, and for the largest one, it's too big, and he's saying it's too much walking to go like around the counter, I guess. The middle one is just right, 10 feet, and it's really easy for him to move. But the smallest one is too densely packed, and although the walking distance is the shortest, he can't make it across. And he's saying like help, because he can't like walk through it, I guess. And the middle thing, the middle bakery, the middle picture of the bakery, we see the recipe for the flatbread, and it shows 6 steps. So they butter the dough, and then they line a mold, they bake the dough, and they peel off the mold, cut the excess bread off, and make it pretty by adding toppings for the 6th step. And the very last slide shows tips for making the flatbread, and it says like it's important to remove any flour or contaminants from the air, which like could like ruin the bread, I guess. And we have to work with enough room, like what the second row shows.
So the whole analogy reveals several scientific concepts in our experiment. So first, let's look at the top area. The top area, it shows the blueprints, and it's actually describing the wavelength and the wavelength and the feature size, the relation between them. So from right to left, we can see that the length of the width is 30 feet, 10 feet, and 5 feet. And it seems that there's only 1 block on the right, 3 blocks on the middle, and 6 blocks on the left. So when the wavelength is the 30 feet, 10 feet, and 5 feet, and when wavelength decrease, and the feature size decrease, and it shows like more fine. And in the middle, it shows about resistance. So like it seems like the middleman, it works the most comfortably. Why? Because the left man, he has a short like width, and the right man has a long length. So the resistance increase when the length increase, and the resistance also increase when the width decrease. So the middleman has the least resistance, so he feels the most comfortable. And let's see the bottom part of this analogy. This 6th process is the 6th process on the photolithography. It is coating photoresist, aligning the mask, expose it to the sunlight, developing it, etching, and stripping. And in the corner, it has the tips. It mentions about clean room. It shows that clean room is an important concept when we're doing photolithography.
All right, so now some of the limitations of this analogy. First, for the last 3 steps on the flatbread recipe, it's hard to show the actual 3 steps in the last 3 steps of the actual photolithography process in this. So for the peel-off mold, really it should be more of like removing the burn-off sections instead of removing like the whole upper layer. And for the cutting off excess, really that would consist of etching deeper into the patterns created, but or here just cutting off all the patterning. And the last one is, I guess, somewhat unrelated. It's more of a decoration thing instead of the last step, which would be, of course, removing the remaining photoresist. The next few issues is that the top, I suppose it's supposed to somewhat include the size correlating to the function. It doesn't do it very clearly. I suppose that for the medium side, it's supposed to be very good for baking. Other sizes not so much for the same functions. And it's really more of that in general, not really lithography. And finally, just to say the few concepts that we covered on that day, which it doesn't mention. These ones would be pretty hard to include in this. Parallel versus sequential processes, which I guess could have been done with multiple breads being baked at the same time, transistors, and scanning electron microscopes. For that, thank you.
Thank you.
Okay, questions from the audience. If I turn behind me, is Dr. Rita Blake raising her hand?
Actually, no, not at this moment.
Surprising. Okay, I have a question. So you guys mentioned the clean room, and you guys actually got to go inside of one yesterday. That was the picture that we showed of them in little bunny suits. So could you describe to everyone what you learned about the clean room? Why is it called a clean room? What are some of the important features of that?
Okay, so the clean room is really important for like the photolithography because when we're doing like little computer chips and stuff, even like the tiniest dust particle or like little strands of hair could be really big on the nanoscale. So even though it seems small to us, it's actually really big when we're like printing these fine little patterns on the chips. So it's really important to keep all contamination away from the air. That's why there's like special venting and stuff like that. You wanna add on?
For anyone who's interested in actual numbers, the size of some of these smaller components on a chip could be on scale of nanometers. That's a pretty small amount. Can't really describe the full thing here right now in the space of this, but the size of a human hair, on the other hand, is in scale of microns. Microns are 1,000 times larger than nanometers, so it would be a pretty bad thing for one to get onto those components. It would probably destroy it.
Okay, I have questions about limits of analogy. And I also just want to make a comment to you guys and everybody else. You know, X idea was not as clear as I want or something. That's not what we mean when we say limits of analogy. What we mean is, where is it just there's a science concept that is just can't be captured by this? So I want to talk about the bottom, which is there's the steps of doing photolithography. And so you butter the dough, so that's like making the substrate and then align it with the mold and then the bake. There is a fundamental concept that is not in this, that is sort of a key part of photolithography.
I feel like the bottom, it only represents 2 layers and not the 3 layers of like a photoresist, a copper, and a substrate, and they're kind of making the bread like the copper and the substrate.
Yeah, but you know, the substrate's just to hold the copper, and bread doesn't need to be held, so it doesn't really matter if they have a substrate. The copper's the important part.
Like, and like the pattern isn't in the end result too.
That's the key thing, is that the whole idea of photolithography is that you are taking a thing and you're turning it into a patterned thing, like you know, there is copper someplace and there isn't copper other places. And so for the future groups, try to just think about the science limitations and say what physics is there. So the idea that you take an active material and you do some mold that in this case creates a shape, an outside shape, which is a shape thing, but it's not an inside pattern. And so the outside shape is the way it's trying to capture that physics, but that's a limit of the analogy. So I just want people to sort of try to think about it in those terms. So maybe think about it this way. When you say this is a limit to the analogy, that must immediately be followed by an explanation of the real science. So the only reason to say there is a limit to the analogy is to give you an opportunity to explain the actual science bit.
So one of the other concepts that you learned that is really cool when it comes to doing stuff with photolithography is the idea of parallel processing. So can you describe what that is and how you could possibly incorporate the difference between parallel and sequential processing using this idea of baking?
Yeah, so the difference between parallel and sequential processing in like an industrial setting is that parallel processing is when you're making multiple different parts at the exact same time and then combining them together at the end, while sequential processing is you do it in order from step 1 to step 2 to step 3, etc. And so in the case of baking a cake, one way you could have parallel processing is while you're making the batter or the dough for the cake or the bread, the toppings, you're making them separately while the cake is baking, And so that way you don't have to make them at the very end and put them onto the bread at the very end.
All right. Thank you, guys. All right. And our artist.
I think they did a really good. Oh, I'm Nico Petrigliano, and I think they did a great job at looking at my drawing. And I really liked how they were able to take apart the recipe and show what I didn't get with my steps, and also the parallel and sequential processing was actually kind of what inspired the bakery idea, and then I just forgot about it while I was drawing it.
All right. Thank you. All right. Group 5. Okay, so I just want to preface with the fact that we did an experiment this morning on plasmonic nanoparticles. And so we had 8 very brave volunteers choose to make these drawings during lunch, so just 2 hours ago. And so 2 teams of 4 made these drawings, and then they switched drawings to talk about. So they just learned these concepts this morning. And they made a drawing themselves, which will be presented later. But they're talking about a drawing that was just drawn, hot off the presses, about an hour ago.
Hi, my name is Alva.
My name is Emma.
My name is Yufei.
And my name's Tura. So today we did an experiment on plasmonics, and the goal for this experiment was to synthesize gold nanoparticles of various shapes and sizes to observe how they interact with light. So we started with a gold salt in its ionic form, and it reacted with sodium citrate under high heat and constant stirring, which formed our initial nanospheres. When these metallic particles are similar in size to the wavelength of light, they interact with that wavelength, and in this case they absorb it. So they present the inverse color on the color wheel. So because we had gold nanospheres and they favor green wavelengths of light, they present red. So in our experiment this morning, we started with a yellow tinted color because of the gold ions, and then it went clear to magenta to purple, or like a red in the end. And then afterwards we tested their stability and attempted to synthesize citrate-coated nanostars to see their effect on color. Okay, so now I'm going to describe what we literally see in this image. So we have 3 rows, and in the first one we have 3 puzzle pieces, and they're all different colors and different shapes and different sizes, as we see with this little measuring tool. And then in the next scene we have 3 puzzles, and they all have a missing piece that corresponds with the original puzzle piece. And then the last scene is all 3 puzzles completed, but they're flipped onto their back, and they display a different color than the original puzzle piece color. And so now we're going to move into the concepts that this image covers. So first, it covers plasmonic resonance in terms of the wavelength. So in this image, that is represented by the length of the puzzle piece, which we see here, a little measurement tool. And so because each puzzle piece corresponds to the rest of the puzzle, it fits perfectly in place and it completes the puzzle in the end.
Okay, and so to add on, when the puzzle is completed, the puzzle is flipped to reveal a solid color that is complementary to the original color. And this kind of relates to our experiment because the puzzle sort of absorbs the final piece with a specific color. So if you take the first one, it would be orange, for example. And then when you flip it, the whole thing turns blue. This is representative of the puzzle piece kind of absorbing the orange light. And so since the orange light is no longer transmitted, it appears to be blue. And in our experiment today, it's similar because when the gold nanospheres were absorbing green light, it reflected the red light. So that's what we saw.
And to address some of the limits of this drawing, so this drawing does not include oscillation, which is this movement back and forth. So, for example, it could be a swing at a park going back and forth, that's oscillation. So this drawing does not address that concept because that is like a concept of plasmonic resonance. And another limitation is that it does not address light transmission and light scattering. Light transmission can be like a light shining through a fabric. When it shines through, that is light transmission. And light scattering can be a sunset, like the sun shining through the air and the blue-green light gets like absorbed, so the sky turns red. It also does not address the photothermal effect, which is a part of our experiment today, which is turning light energy into thermal energy, which is heat. So this drawing does not include that fact. And also another limitation, like on the science part, is that in the drawing it is absorbing the orange light and then turning the puzzle over, that's like the blue light. But like in the experiment, it was like the liquid was like, it had like green, it was like green, it absorbs the green light, so it was like reflecting a red light.
Questions from the audience? Slowly giving you time to have questions.
You can save them.
All right.
So one thing that you guys mentioned was the oscillation. Can you describe that in a little bit more detail? So why is the oscillation important and how does it relate to the colors in the experiment? Right, so what is oscillating with what? Because you mentioned a swing, so that's something that's moving back and forth. So can you then elaborate on what is why, I guess I'll start with, why whatever is oscillating and what is it oscillating with?
In plasmonic resonance, the electrons on the metal's nanoparticle surface are oscillating, and this makes it like it amplifies it, which makes it easier for to be used in nanoparticles. And you're partway there, right? So you got it right that they're metallic nanoparticles and the electrons of the surface are what are oscillating, but you also said resonance, right? So what's the difference between oscillation and the resonance?
But first, why are the electrons oscillating?
Yeah, better way of phrasing it.
Why? So oscillating means going back and forth. Mm-hmm. So in that swing analogy, there's some dude pushing the child. Mm-hmm. that's the only way the swing goes back and forth. Some random person, maybe parental in flavor, is pushing that child. So the question is, the electrons are going back and forth. What's pushing them?
Well, the right wavelength would excite the electrons.
So it is light, that's right. So what is it in the light that is pushing the electrons? What is light? What is light? Huh? A wave? It is a wave. It's a wave of what?
Energy?
It carries energy. But, so, we have a picture wave, up, down, up, down. What is upping and downing? What are those things that are going up and down? What fundamentally is light?
Like electrons? Like
Huh?
energy, like electrons kind of, like energies? Like
So light is not electrons.
Right.
So the light wave itself.
Like the light particles that are like carrying energy?
So there is this whole wave particle duality, and you can think of light as a photon, but I would recommend against the particle picture at this moment in time. I think that the wave picture will help you a lot more. So just stick with it's a wave. So something is going up and down and up and down. What is that something that is sort of the core of what light is? So maybe I should say, light is visible light is an example of radiation. What do we there's a word we use to describe the whole electromagnetic. So that's the key to what's the up and the down. So based on that electromagnetic, what might the things that are going up and down be?
The electromagnetic wave of radiation.
Right. So what is the electromagnetic? What does that refer to?
It's the oscillations between electricity and
It's two things. It's got an electric one and a magnetic one. So you don't need both.
it's the perpendicular oscillation between electrical and magnetic fields.
Fields! They're electric fields! Yes! The light is a bunch of oscillating electric fields. So what is making the electrons slosh back and forth?
Magnetic field.
Electric fields. Electrons respond to electric fields. Magnetic dipoles respond to. We're not worried about the magnetic part. Less weaker, unimportant, really complicated. Just ignore the magnetic part. Okay, so it's an oscillating electric field. That's what's making the electrons move. So now we go back to Rita's question. What is this resonant thing? Because that's sort of the whole key idea of this. You said when they're in resonance. What does in resonance mean? Just say, it doesn't matter if it's wrong. Just say whatever you're thinking.
I was thinking back to the swing analogy, and the driving force is that under one specific length, then they're driving that distance back and forth, but only in that one wavelength.
That's exactly right. When the electric field, like the swing, can push the electrons back and forth, and they can go back and forth, and there's a new push from the electric field, whenever there's like a new push from the swing, that's when the light gets absorbed. Okay, we're out of time, but I'm going to ask my last quick question. Why are the different, with that picture, why are the different shapes different colors?
You want to go for it?
So like that kind of represents the different colors in the light and the different colored wavelengths in the light that are hitting, that are being absorbed by the different things in the liquid.
So if you go back to the swing analogy, if you had the different shapes of particles would be like a swing that was different how?
Well, it could have been different heights of the swing.
Perfect. Awesome. There's cool physics here, and you guys did a great job.
All right, thank you. Okay, and our artists were group 10, who will present later. But did you guys, are you all over here? I know some of you are. Okay, yeah. So did you guys have anything that you wanted to add? Did they cover it well?
I think they covered all of it very well.
Thank you. All right, so now we are going to take a brief intermission. Let's be back by 3:25. All right, perfect. Thank you, Dr. Rita Blake.
basically constant across the particle. So it's sort of the opposite. Yeah, it's important that the wavelength is not the same as the particle size.
The wavelength, yeah, exactly. It's just a static field.
Yeah, but it's so complicated. Like it's impossible to actually like get those details.
But at this point, the key thing is just that the color changes because if you have a round thing, you can just wash equally in all directions. Right. You have a long skinny thing, you have one sloshing after and one sloshing, and that's what makes it a different color. Yeah. So it doesn't matter if you're little round or big round, as long as you're smaller than the light. Yeah. You gotta be little. Yeah. But as long as you're little, it doesn't matter if you're sort of little or big. Yeah. The color difference is that as you get big, it starts to scatter. Yeah.
All right, let's find our seats, please. Okay, we're gonna get started again. So we have group 6. Come on up. Two handhelds. All right. Laser pointer. All right.
Oh, just a quick PSA for all of our presenters. Please don't be to this side of the step and repeat, because if you are too far to this side, we cannot see you on the live stream and you're cut off. So just try to be within range. All right.
Hello, my name is Dea, and I'm from California.
Hello, I'm Ali. I'm from Turkey.
Hello, I'm Bo Junzhang. I'm from China.
So this is an analogy which is meant to represent the experiments that we did on our first day. These were already described before, but I'll review them again. So what we did was we focused on how we can measure objects at the nanoscale which are not visible by manipulating their properties or observing them indirectly. So we looked at the diffraction grating, which is essentially a piece of plastic with really, really small nanoscale grooves in it. And by shining light through it and watching the light scatter, you can see where the grooves are and about how large they are by kind of reverse calculating. And this is one example of many different ways which we learned about, especially like using microscopy to figure out the properties of nanoparticles and characterize them without like just burning your eyes out staring. And one of the concepts that we learned about a lot was this idea of constructive and destructive interference, because when the light goes through the diffraction grating, parts of the light will, like all the light gets spread out and waves will coincide with each other. And where they coincide, where they're both at a peak or both at a trough, those two waves will combine to form a much bigger, like stronger wave. But if the two waves coincide with each other on opposite ends of their cycle, then they just cancel each other out and you end up getting nothing. And so where the waves are constructively interfering, you see light, and where they're destructively interfering, you don't. And based on that, you can figure out like the angles of the light and determine how large the grooves are without like looking at it.
All right, so I will be explaining what is literally I'm seeing in here. So in here, there's a wind that is contributing to this warship to go faster. So that is saying, look at the flags. They indicate strong winds. We should go. Say this wind is a contribution for this warship. On the other side, there are two warships, maybe from USA. I don't know. There are friendly forces. Let's just join together. So they made a team by this. On the third part, we see like one team in here, and they're saying there are enemies 5. So there's a pirate ship in here. So this is going to attack them. So this is what is going to happen. And on the end, like both of the ships gonna sink. I don't know what it is, but like there are 2 of them and one is here, but both of them are sinking. I don't know. Maybe it's the thing of the ships.
Yes. So, what concepts are presented? First,
is about the indirect measurements. Like we can see the first picture, the wind blows up the flag. The degree of the flag blows up reflect how strong the wind is. And for the second picture, we can see two bolts they are meeting together and become a friendly force. That means the constructive interference. When two waves are meeting together, peak to peak and trough to trough, they can become a stronger wave. And the third picture, when they meet a pirate, they're going to fight. That's the destructive interference. A wave meet a opposite wave, peak to trough and trough to peak, then they just canceling out, so resulting all of the boats are sink. Yes, so that's the result of the destructive interference. They become a line eventually.
Yeah, so this is a really great analogy because I think it like shows it in a very intuitive way. But the limitation, the biggest limitation is that the waves work in a very specific way where they are literally just like canceling out into a flat line and zero, rather than coming into conflict and then it resolving in like the destruction of the waves. So this isn't exactly how waves actually operate, like if they're all flowing in the same field. So the analogy, while it's like really good, it's not totally clear, and also like it's not totally direct, especially because like ships, like they don't have to sink. Like someone can win. That's not necessarily what happens in this case. Whereas if you have two opposing waves, literally you just don't see anything. But yeah, thank you. Do we have any questions?
Questions from the audience? All right, go ahead, Sarah.
Okay, I totally agree with everything you said, that I'm going to ask the same hard question that I asked the other group who did this, that the wave nature is not, the idea of destructive interference and everybody just going away, you know, if you're trying to convey that to, you know, your little sibling who has no idea what an electromagnetic wave is, that's a good way to do it. Is there any way you could think of to use this ship analogy to get across more of the physics of destructive interference, where, you know, we got that light is an electromagnetic wave, and so like the destructive interference is actually one electric field's going this way, another electric field's going that way, and you end up with no electric field. So I don't have a brilliant answer, but you guys are creative people. Is there any way you could put that in this picture?
I think the best analogy that we could think of is like if you want to continue with this idea of ships that are fighting each other. I guess narwhals do this, I don't know if ships do, where they like lock into each other and they're like pushing back and forth. And so I think if the two ships are on the water and they're trying to kind of push each other in opposite directions, like they're not going to go anywhere, right? Whereas if they're both pulling in the same direction, like both putting their motors in the same direction, then they would be able to like go further and faster.
That would be a great way to capture that concept with ships on an ocean. Very good job.
Okay, I think that's the only question. Yeah. All right. Who is our artist?
I'm Selena Zhou, and I think they did a pretty good job, and thank you.
All right, group 7.
So, I'm Imanch, I'm from Bellevue.
I'm Jackie, I'm from LA.
I'm Selena, I'm from China.
I'm Gavin from China. So this experiment is dye-sensitive solar cells. We did this, I think, on Wednesday, Tuesday. But basically, what happens in it is that there's it's a solar cell, so it takes light from the sun and converts it to electricity. So how it does that is it has this coating of TiO2, which is titanium dioxide, and this is white, so it doesn't absorb visible light, so it reflects. Oh, so it reflects everything, and then you can't really get any energy out of that if it reflects everything. So you have to attach dye to it. So in this, we used, I think it was raspberry juice, which contains a sort of dye which is like purple or reddish, and then you dip the TiO2 covered glass plate into it. And so this glass is conductive, so it can conduct electricity that's generated from this. So then you put iodine on top of the dyed TiO2. And this basically, all the electrons that go in the circuit, it replenishes the electrons that are taken from the dye. And then you put graphite on the top piece of glass, and this acts as a catalyst to promote like iodine from going from, I think it was I minus to 3I minus. Yeah, and then basically the electrons from there go into a cycle. You'll be able to see it more clearly in that, and through a circuit, and they come back, and it repeats.
Well, in this picture, we can obviously say there are two beds on the wall in the theater, and they are getting enough energy, so they fly around to terrify the children. The children run away past the stairs. At the same time, there are three new children coming into the theater, and they found there are some empty seats, so they want to sit here. Then the previous children maybe they go away by taking the taxi or a car, and also meanwhile in the theater, the new children are scared by the bats. Yeah.
And here is our interpretation. We think that in the solar cell, the sunlight is the energy. So in this picture, the bats is that who lets everything happen. And then the dye in the solar cell is to absorb the energy and activates the electrons. So in these pictures, the mom, we think it is the dye who first surround the children, and then the children is terrified by the bats, and the children are released. So the TiO2 is where the dye attached. The mom sits on the seats. So the seats is the TiO2. And the iodine supply the electrons. So we see at the bottom there is a car, and when the cars go in, it supplies new children into the theater. So the car is the iodine. And also the graphite. The graphite serves as an catalyst, which helps the electrons to get excited. And in these pictures, the steps who helps the children to get up, and which is the electrons get excited, is what we think it is the graphite. And also the electrode. The electrode let the electrons go into the circuit. So we think that the door let the children go into the theater is the electrode. Also, the road is circular, so it represents the cyclic nature of energy flow, and the current is the movement of the charge. The kids go through the road is current. And the voltage is the electric potential difference. And when the children goes up into the stairs, this creates a potential difference. And that's all. Yeah.
Some limitations to this drawing is that we are unclear of what the sugar rush is, because since it represents the sunlight, since the bats represent the sunlight, we during the experiment we didn't change the sunlight in any way. And another one is that
the storage is not included in the drawing, and they can maybe add a storage like to hold the electrons.
All right, questions from our audience, please.
So when we were looking at this drawing, the instructors, we actually interpreted the sugar as the sunlight. So if that were to be the case, could you then sort of reconfigure your thoughts on what the rest of the drawing would be like if the sugar is meant to be the sun? And why the sugar would be the sun?
Just say yes. Let's just say for a moment, yes, the sugar is the sun. And then say, what is the sugar exciting? And then go from there.
So if the sugar was the sun, then the sugar would be exciting the bats, which is the dye. And the dye would have electrons and it would like give up its electrons, and they would like go along the circuit. So the children would still be the electrons, just they'd be excited by the dye.
I think that would make sense.
Yeah. Okay. So my other question is, you pointed out the circular nature of this, which is really important. There's an aspect of the circular nature that isn't fully captured. Can you talk a little bit about that and what you could possibly change to include that concept?
So I think one important aspect of the circular nature is that there's a positive and negative electrodes. So in our experiment, we had 2 glass plates, and one of them was positive, one of them was negative. So in this, if you see, the theater only has 1 door, so it doesn't really like capture how electrons, I think, flow out of the positive into the negative, right? But in this, it goes from the door back to the door. So that might be one thing.
So what are the children you said are?
Electrons.
Okay, and so you start with children in the theater, electrons in the titania. It's all the same, of course. What do you end with?
You end with new children in the seats.
You end with new children in the seats. In the actual solar cell, what do you end with?
You end with the same electrons.
Yeah.
These are the same.
These are the same.
Oh.
Because it says meter
Oh, all right. So in the actual solar cell, the iodine supplies new electrons to it. But here, I think they just like go back and they go back to their seats.
Okay, that's awesome. Yeah, that is the full circular nature, that the iodine supplies new electrons to the titania, but then the old electrons go back to the iodine. And so that component is actually all there. Good job.
Of course, Dima.
Okay, so I absolutely love this analogy. But yeah, I agree. There is one other component as well of this circular nature of the solar cell that's missing, or more precisely, like what would electrons do once they leave the solar cell on their way back to the solar cell in the circuit? Like in an actual circuit, what's the point of exciting electrons?
It's just it's just to like power the circuit, because like if you have an LED or like a motor, you need electrons to flow through it to spin it or light it up or
Exactly, exactly. So the selectrons would do some work, right? It would do something useful. And actually, on the previous drawing, we had that, what was it? Treadmill, exactly. Yeah, here it's kind of, they're just driving around and going back. So this is a short circuit where they don't do anything. Yeah, okay.
But physics-wise, you could just explain this. You could say, this is a solar cell, but this is a short-circuited solar cell. I think you actually probably did short-circuit your solar cells to measure the short-circuit current. And so we do short-circuit solar cells, and that's what's drawn here. So you could explain it. Awesome.
Okay, good job.
All right, and our artist.
Yeah, I'm Dea. You just saw me. Thank you. That was really good. I'm really, yeah. I think that you got it mostly right. I think the candy, it does have a sun on it, so I think that was meant to be like sunlight. It was then like getting the bats excited, and then the bats were passing on their excitement to the kids, and then the kids were like running around. I think it. I think it's a little confusing because, like, the bats are like scaring the children, and then the children just kind of run away. But I think you guys did a really, really good job of like explaining it. I don't think I would have been able to explain this, so I really appreciate that. Like, thank you guys. You did a really nice job.
All right, thank you. All right, group 8.
Hi, my name is Ava Wong. I'm a junior, and I'm from Chino Hills.
My name is Andrew Deesum. I'm a rising senior, and I'm from Torrance.
My name's Max. I'm from Connecticut. I'm currently a junior.
My name's Jasper. I'm going to be a junior at Palo Alto High School.
First, we're going to talk about the context of our experiment. We designed and tested a glucose sugar, which is sugar, biosensor using an enzyme-based nanoporous bead to detect sugar concentrations in an assay of various solutions compared to unknown samples. Our enzymes that we used were horseradish peroxidase and glucose oxidase. And an assay is like a tray used to hold our solutions. And it resulted in various shades of pink representing the sugar concentrations in the sample.
So looking at this picture, we literally see, so this is a guy holding an apple with like a little bit of brown on it. And he's asking, how old is this apple? And if you go over here, you see a table with like 5 different apples, each with like different amounts of brownness on it. And above it, there's like the amount of time it's been out in the air. And over here, you see a guy blowing, he's blowing on the apple. And while he's doing this, he's saying, by blowing on it, it turns the apples brown faster. And to the right of him, there's a guy with a shield saying, I will protect. And he's basically just protecting the table and this guy blowing the apples from the guy holding a knife because he's trying to kill him. Over here, this is the same guy for like, these are the same guys. And based on these apples that he sees on the table, he matched the one that he has with the ones on the table. So he came to a conclusion and he said, based on the color, it must be 10 minutes old. He just matched it.
This analogy covers a lot of scientific concepts. Firstly, like the definition of the sensor and the steps of the sensor. In this case, basically colorimetric sensor, which is transfer a signal into another signal that is easy to read. And for the first step is signal. It's right. Oh. The first step is signal is right there. Like this one is holding an apple with a brown dot. And the transduction, this when hold this apple with the brown dot compares to the like sheet-like things, which is called colorimetric, which is called calibration curve, and the and the response, which is right there. Like he compares that he find out that this brown dot take 10 minutes to form, and this also talks about the importance of encapsulate enzyme reaction into a nanoporous speed. Like in right here, the man with the shield and the man with the sword. Like the man with the sword is basically the factors that cause enzymes to denature, and the man with the shield, which is the nanoporous bead that protects proteins from denature. And also this talk about enzyme. This one who is blowing air to the apple is enzyme is a protein that lowers the activation energy of process, which speeds it up. Enzymes are not consumed and are specific to certain molecules. They can denature if their bonds are broken. In this case, the person blowing the apple is the enzyme. Yeah.
Okay, so the last concept that's described here is a calibration curve. And now Max already explained a little bit, but basically a calibration curve is using several known values of something to identify an unknown value. And in this case, the known values are the apples up there with different times, and the unknown apple is what the guy is holding and trying to find the age of. Now, this is a very simple and effective analogy, but there are some limitations. And one of the smaller things is that the apples could be spaced out a bit more linearly, as in like with consistent intervals in between. And one more thing is that the person blowing, which is the enzyme, is speeding up the process, but he is not reducing the energy needed to turn the apple brown, which is what an enzyme does. Thank you.
Questions from the audience?
What do you think the guy with the knife is trying to do?
Basically, that's just like a representation of that the outside stuff trying to like denature the enzyme.
And in context of the drawing, it's trying to attack the guy blowing the air.
So, in your experiment, you said you used 2 enzymes, right? So can you elaborate then on what that indicates about the sort of type of sensor this is? And how is that, because there's one other thing I think between that process and this process that is a little bit different. So a typical sensor is signal, transduction, response. So if you have 2 enzymes, what does that mean?
What do you mean by like 2 enzymes?
So is it always just one time, one signal, one transduction, and one response? If you have 2 enzymes, why 2 enzymes? Why not just one enzyme? Why do we need 2 different ones?
Well, during the experiment, we used the enzymes to compare different ones if we use the same test. But in this case, we're only covering one of the enzymes.
Right. So in the real experiment, you're using 2 enzymes. Are they doing the same thing at the same time? Yeah. Can you actually explain the assay a little bit more that you did?
Yes, so we did the 2 enzymes, and there were multiple of these processes, not just one happening at the same time. And so we wanted to compare those results from the responses. And so during the transduction process, the enzyme did different things to speed up the reaction. And so having the 2 enzymes have different results made it able for us to compare them.
Okay, so you have a substrate. And what you want, you put something in, and you get a color out. Okay, so in this case, and an enzyme does something or some enzymes do something in the process. So right here, what you have is a cut apple. That's what you put in. Oxygen comes in to do browning, oxidation reaction, and what comes out is an amount of brownness. In your system, you put in glucose, and then what happened?
Name your enzymes. What were the enzymes we used? What was the first one?
Horseradish peroxidase.
That was not the first one. What was the first one?
Glucose oxidase.
Glucose oxidase. Okay, so you input glucose. What does the glucose oxidase do?
It oxidizes.
It oxidizes what?
It oxidizes the glucose, just like the name.
Yep, exactly. And so that's so you know, blowing air, that's oxidation. That's good. So that's another sort of concept. So there's an oxidation. But in an apple, oxidation makes it brown. In glucose, after you oxidize it, what color is it?
It makes it like pink.
No, it doesn't make it pink. So how do you get the pink?
By like getting different kinds of enzymes like this, like it
So-
like have some sequence in it.
Yeah. So what was the second enzyme? You already said it.
Horseradish.
Horseradish
Peroxidation.
peroxidase. So horseradish just means it came from a horseradish, so that's sort of irrelevant. Any idea what peroxidase means? You don't really need to. Vaguely, what kind of reaction is it probably doing?
Like give colors to indicate the results.
It's doing more oxidation. And then how do you get color?
Okay, so we had our glucose and our glucose oxidase. It was glucose plus water with the glucose oxidase produces that glucose with the ketone on it plus it's important for the peroxidase part.
The horseradish?
No.
The other half of the name. The peroxidase. Peroxide.
So we had our glucose that was oxidized, and then we also produced hydrogen peroxide. Then that hydrogen peroxide mixes with our two dye molecules that are initially colorless, and the horseradish peroxidase combines those two dyes with the hydrogen peroxide, and then what do you get? Well, you've been saying this whole time, what do you get?
Color.
You get the pink color. Great. All right, that's all we have time for. Okay, so who is our artist?
I'm James, and they pretty much got all of it. There was more stuff that they said that I was honestly trying to include, but I just like happened to include by accident. And then also the limitation, they were completely right about that. I just put random times, and they probably should have been spaced out. But yeah, they did a great job.
All right, thank you. All right, group 9.
So I just want to point out, when people do time sequences, things actually slow down as they keep going. And so it is very common to do short time intervals and then get longer. So you actually put it on a logarithmic scale, and that is what this author did. So evenly spaced is actually not the best way to space time points. The close together at the start and then spreading out as you go longer is an awesome way to space time. So remember that if you're measuring horseradish peroxidase in the future.
Or apples.
Hi, my name is Thatcher, and I'm from Santa Monica.
I'm Brandon. I'm from San Francisco.
I'm Jay. I'm from Santa Clara.
Hi, I'm Coco, and I'm from Seattle.
So for the topic that we are covering, we are talking about photolithography, which in this experiment, we're exploring like the process that's typically used in semiconductor production, like transistors for computers. Photolithography involves the process of creating a pattern on the material called a photoresist. And you use the photoresist to apply it onto a conductive surface. And you shine UV light on the conductive surface to basically cure the photoresist, where you can then dip it in a solution to dissolve away the unnecessary parts of the conductor pattern so that you can basically get rid of the excess conductor to leave behind a pattern of the circuit or the circuitry that you want on the conductive surface. And typically this process is favored over just like typical etching because you want very small circuits for smaller computers like phones and smartwatches. And on the nanoscale level, you can put a lot of circuitry in a small board, and that's what photolithography is typically used for.
So this drawing uses an analogy involving a jack-o'-lantern, and at the top you can see a pumpkin that goes through various steps and stages, and this includes placing a stencil, cutting with the tool, removing the unwanted sections by scooping out the inner parts, and lighting it up using a light bulb, and finally closing the jack-o'-lantern. And in the middle you can see that there are some jack-o'-lanterns from 1970, 1972, and 1974, and they each have a different number of teeth. And they are carved using different sizes of knives, which reduce in size over time. And on the bottom left, there is a person that drops a rock onto the jack-o'-lantern, and this breaks it. And on the other side, there's a close-up of the jack-o'-lantern.
All right. So the top image up here shows the steps of photolithography. So basically, wait, hold up. What's the laser pointer? Oh, right here. So this pumpkin, blank pumpkin, it represents the blank wafer of a computer chip. And drawing this face on the pumpkin represents like applying the mask to the chip, and cutting it out is kind of similar to developing the photoresist, and scooping the insides out of the pumpkin, like over there, represents etching, where unwanted material is removed. And finally, the glowing jack-o'-lantern at the end represents the finished chip that's ready to work. And this middle left image over here shows how photolithography can be scaled down in feature size. So the jack-o'-lantern faces, as you can see, they get slowly more detailed as the tool used shifts from like a cleaver to a kitchen knife to a buzz saw, which is somehow more precise than the kitchen knife, but I don't know. So this middle right image here, so it represents Moore's law, which states that the number of transistors on a chip doubles around every 2 years, which is represented by the pumpkin having one tooth at first, then 2, and then 4. And then this image on the bottom right with the really tall dude that's apparently a mile tall, it represents the importance of a clean room. So this huge guy represents a dust particle, and even though dust seems small to us, it's actually really, really big on the nanoscale and can wreck a chip during photolithography, and it's why clean rooms are important to avoid having big dust particles like these dropping rocks on your jack-o'-lantern and breaking them. Yeah. So finally, the bottom image shows why we use electrons instead of light in a scanning electron microscope. The big knife here represents visible light, which can't see anything smaller than around 250 nanometers due to diffraction. And the small knife here being thrown by that guy represents a electron beam, which can focus on much tinier stuff and let us see small things like viruses. And the mask being drawn is kind of like the image being seen through the microscope lens. Yeah.
Okay, so some limitations of this analogy is that it doesn't clearly represent a transistor, which are semiconductors used in computer chips that can be turned on and off to represent binary code. And one easy way they could add this is maybe next to the jack-o'-lantern, they could add a switch that says on or off, and you could control the light. And one other limitation that we noticed as a group was that there's no clear parallel processing. So they do a good job of representing sequential processing by the steps over here. But they can maybe show parallel processing, like when they're creating the mask, someone else could be scooping out the pulp in seeds of the pumpkin.
All right, questions from our audience.
Okay, so parallel processing of jack-o'-lanterns is actually sort of challenging because they are intrinsically a serial process. So having someone else scooping out the pulp on the same jack-o'-lantern is not actually parallel processing. So first question is, what would be parallel processing of jack-o'-lanterns? Or what does parallel processing mean, just in its basic form?
In its most basic form, it would be where potentially two different steps of a single process is done at the same time, so that they can be combined later to save time instead of doing each step sequentially.
So that's actually not really the big idea. The big idea, so in a computer chip, so how big is a computer chip?
This small, it could be this small.
Teeny tiny. How big are the silicon wafers that are used in processing?
We saw like 8-inch discs
Yeah,
up to.
big discs. So that is parallel processing. So what's on that big 8-inch disc?
Oh, there's various transistors on.
Yeah, there's gazillions of transistors, but there's a whole pile of individual chips. So there's like a whole ton of individual chips, and then later they take a wafer dicer and they cut them all up and they make each chip. So why do they do that? Why do they do it on a great big wafer instead of just making each chip one at a time?
Because making each chip one at a time, you would have to combine them at a later step, which could take time or materials. And doing all the chips in a single wafer would save time.
Right. So for each step that they're doing on chip 1, at the same time they're doing it on chip 2 and chip 3 and chip 4 and chip 5. So it's not combining 2 steps. It's doing the first step on all the chips and then doing the second step on all the chips. So with that in mind, what could possibly be parallel processing of jack-o'-lanterns? It doesn't have to be realistic. It can be like any crazy idea you want.
Well, you could have like a jack-o'-lantern making competition where like everyone is making jack-o'-lanterns at once. Like, I don't know.
Yeah, it could be a whole bunch of people all making jack-o'-lanterns together. Or it could be an octopus with 8 arms and 8 knives cutting 8 jack-o'-lanterns at the same time.
Yeah.
But the concept of parallel processing is that each step you're doing many times over all at the same time, and then you do all the next steps. Okay.
All right. Thank you, guys. And our artists, please.
Wait, you forgot your.
They're doing really great. About the 2, because I never made a jack-o'-lantern, so I don't know about the 2. So I just never.
All right. Thank you, guys. All right, group 10. This is our last group to go. And again, this was the group that drew group 5's image. So again, they're covering our plasmonics experiment that we just did this morning.
Hi, my name's Ashley from Lynbrook High School in San Jose, California.
I'm James, and I'm from LA.
I'm Yuchen, I'm from China.
I'm Nico, and I'm from here. So this morning we learned about plasmonic nanoparticles, which sounds really complicated, and it is really complicated. But it's something that the Greeks even sort of knew about with their stained glass windows. They ground up different metals and put it in the glass, which changed the color. And the reason why they're so special is because these particles are made of metal, so they have electrons, which let them interact with the magnetic field that goes through them when the light shines through them. And so today in our experiment, we tried a variety of different solutions and mixed them together to see how it changed the size and shape of them, which affected the color.
and now I'm gonna introduce what I'm seeing of this graph. First, there are three graphs of like a single coffee stand selling coffees and hot chocolates. In the first graph on the left, we can see that this person, the seller, is calling like, "Come and get your hot chocolate," and some children are rushing here to buy these hot chocolates. And we can see a thermometer on the right top corner, and it shows the temperature is really cold. In the second graph, the seller is selling some hot coffees, and he is shouting that, "Come and get your coffees." And some adults are like flooding in, and they are going to buy these coffees. And the thermometer in this picture is also very low. Yeah, in the third graph, the seller is run out of coffees and hot chocolates, and all these children and adults are drinking their drinks. And one of the adults is saying, "We're so warm, much warmer now." And we can see that in the thermometer, like it shows a very high temperature.
Okay, so now we're going to look at the analogies and how they relate to the science. So the first part of it is the plasmonic resonance, which basically in the actual science depends on having the matched size and the wavelength of the light and the size of the nanoparticle so that it will actually resonate with the thing. And so then the analogy here is basically the type of person, which is like the children or the adults, which is matching up with the type of drink, which is the hot chocolate or the coffee. There's also the idea of how the size can affect the color when it has to do with plasmonic resonance, because basically the people in this case are different sizes with the children, the adults, which then affects which drink they want. And then another thing that's shown here is photothermal effect, which is basically when the light interacts with a nanoparticle, it produces energy, which is then converted into heat. And so in this case, the light is the drink they're having, which is the source of the energy. And so then that is then converted into heat because when they drink the drink, it's a hot drink. So then they're warmer.
Okay, so now let's talk about the limitations of this analogy. One limitation is that it shows no oscillations. Another thing is that it doesn't compare the light scattering and light transmission. This is a really good analogy, but with some analogies, there's always things that are limited. And in this analogy, it doesn't compare the two of them. So light scattering is where these light waves bounce off of the material, and light transmission is how the light waves go through and absorb by the material. And from here you can tell that the humans are absorbing or they're drinking the hot chocolates or the coffee. However, it's not demonstrating light scattering because you don't see the coffee or hot chocolate bouncing off or coming out of the human. So another limitation is that there's no color. So when two frequencies and light waves correspond, the complementary color would appear. However, since this is a black and white photo, you don't see any color, and thus it can't demonstrate the complementary color that should appear. In addition to this, because there is no color being seen, the color we see really depends on not only the size but also the shape. And this is not demonstrated because, again, there's no color in this. Thank you.
Oh, other students? It's an instructor. Sorry, guys. I think you guys did a great job today. I just wanted to, if you mentioned that shape wasn't included, can you think of a way that they might have incorporated the difference in shape then changing the end outcome?
Yeah. So with this example, they have kids, which are smaller, and they end up fitting with the hot chocolate because it's sweet and they enjoy it. And the adults are bigger, and they work and they get tired, so they need coffee to keep them up.
I think to add on to that, you can also demonstrate the shape by the size of the cups. So you know that kids are smaller in size, so then the cup might be smaller, versus for adults, the coffee size cup might be bigger.
So I want to actually just clarify a little bit of the physics. So the color change is actually much, which I think you saw, is much stronger with shape than with size. So size is sort of a secondary effect. And so to best map this onto the real experiment, I mean, children are not actually just small adults. They have very different aspect ratios in terms of like legs and heads and eyes and everything else. And so the shape effect could totally be captured in children. But I just want to point out, because in the experiment you guys talked about sort of shape and size mixed together, but size is a very weak effect and shape is a very strong effect. Okay, so can I? Yeah. Okay, so you talked about, you said that the scattering was not included here, and you explained the fact that scattering is actually very strongly affected by size, and that this was all absorption. They just took in coffee, which is absorbing, or hot chocolate, which is absorbing the light, and then they heat it up. So my question is always, since you pointed it out, how could you imagine putting scattering, which is light bouncing off, into this picture? Oh, you didn't do any scattering? Okay. All right, you didn't do the end of the experiment, so I'm done. But you talked about it a little. So you could still imagine. Since you did say, you said enough to show that you understood it at least a little bit. Yeah. So how could you imagine putting it into this picture?
Putting into this picture, like one way that you can show that scattering is by maybe spitting out that hot chocolate or coffee, because maybe it just doesn't taste as ideal as you want it to be.
Absolutely. Spilling or spitting would be totally perfect.
So you guys actually said something that inspired a question. You said the Greeks knew what they were doing. And I think that's partly true. I think they knew that they were doing chemistry that produced that beautiful red color, but I don't know that they could see the actual particles that they were making, right? Because can you see nanomaterials with the naked eye? No. Can you see them? Like, how big were the particles that you made? Do you know?
Really, was way smaller than a human hair.
But like in terms of the actual nanometer size, did you guys actually discuss that?
50 nanometers?
50, you said? Ish? So, yeah, so can you see that with a normal microscope?
No.
Probably not, right? So you guys got to tour all of these beautiful facilities here where you guys got to see a bunch of different instruments. Can you describe maybe one of the instruments that you could use to actually visualize the particles as they are in shape and size?
Yeah, so one of the microscopes that we saw was like a transmitting electron microscope, which basically just like shoots electrons at the sample, and then basically it like passes through the sample, and then using like data gathered through sensors, you can then see what the sample was. And the way this works is because basically electrons, similar to light, also have like wavelengths, except their wavelength is a lot smaller than light. And so light's wavelength is actually just too big to see nanoparticles, and so you need something that has a much smaller wavelength to be able to visualize what's seen here.
Yeah, great. Excellent. Okay, and then group 5 were our artists. Did you guys have any comments on things that they might have missed?
I think they covered most of what we were trying to say, especially after the question about how size and shape affects the resonance and how it works. I think that was one of the things we wanted covered, and then they managed to do that after the question was asked. So good job.
Awesome. Thank you, guys.
All right, so that was our last presentation. So congratulations to all of our students. So we have some closing remarks before we go and eat food, our favorite part. So, we had you guys for 1 week here, but, you are our students forever beyond this. So we want to help you succeed. So we would love for you to stay in touch with us. We love to hear all the great things that you guys go on and do. So if you're going to college, university, getting a PhD, now that some of you know what that is, an MD, whatever. But or starting a business, because you guys heard from Professor Dino DiCarlo about taking our ideas all the way to the market. We also have these other great programs like our Nanovation competition, which combines nanoscience and entrepreneurship, and our other summer session programs like applications of nanoscience and nanoscale microscopy. And as I've said many, many, many times this week to coax you guys into participating more, we write letters of recommendation. And so, we cannot guarantee that we will get you into UCLA. That is not a thing. In fact, the UCs don't even accept letters of recommendation as part of the application. But if you need a letter of recommendation for the other colleges and universities that you're applying to, other summer programs, internships, things like that, we would be happy to write you a letter of recommendation. All you need to do is email me, and we will get that process started. So again, we want to help you guys succeed, even if it's later this fall, next year, in a couple years from now. Please keep us in mind. And then, one of our goals for this class, our goals in life, is reflection and introspection. And parents, if you're here, you can go out into the lobby and you'll see all these Post-it notes that we have along the window. And every day I had your students reflecting on what they've learned, how they've implemented these skills, and things like that. So again, I know I had you do it this morning, reflecting again, but I'm going to have you reflect again now. So take a moment to reflect and think about what you knew about science before you started this course, just a short 5 days ago. And what did you learn over this last week about science, nanoscience, what it means to get a PhD and do scientific research, about science communication, about teamwork, which you did a lot of this week, and more importantly, about yourself, because you all just did a really, really hard thing. And, we are so very proud of all that you've done, but you guys should also be proud of yourselves. So deriving some of that from yourself is also very important. Instead of this external validation, you should be building that internal validation yourself. So please take a moment to reflect. You guys did an amazing job, and we are so, so proud of you. I know a lot of you were discouraged throughout the week with getting probably the lowest score you've ever gotten on a thing in your life, because you are all amazing, excelling, high-achieving students. But you all really worked hard and persevered through those failures to achieve really great things. So again, we are so proud of you, but you should also be very proud of yourselves. Okay, and then lastly, we have some surveys. So of course, thank you to our students. You all did a really great job. If we could give a round of applause to our students. But we are always trying to improve these courses, and there will be some changes in the next years in how UCLA and UCLA summer sessions allows us to run these courses, and so it's really important for us that you take these surveys and fill them out so that we know what's most important for you and how we can continue to operate these classes and give you guys what you need and to take away from this. So I will, of course, email these out to you guys as well, but if our students can take these surveys. And then my last big thank you is to our parents. So parents, this is an amazing opportunity that you've let your students participate in. It's always really important to nurture their interests and let them experience new things. I know that when I was their age, I did not necessarily know well, I didn't know at all what a PhD was, but I didn't know that I wanted to be a scientist at their age. So allowing them to experience these things and see if they like it, if it's something that interests them, is super important. So we really thank you guys as well. And we also have a survey for you as well to complete. So thank you. And then Professor Tolbert, would you like to say some closing remarks? And then we'll just have an announcement about the photo.
Okay, so I want to just take a second. I know that not too many of them are here, but I would like to ask all of our graduate student instructors who are here, can you stand up, raise your hand, and I want to give a big round of applause for the folks who did all of the day-to-day teaching in this class. And then the last, I want to thank parents. I want to tell you, my kids did this. They still remember it. It definitely made an impact on them. And then I just want to take the last opportunity. I want to thank first Dr. Rita Blake, who is our education lead from CNSI. And then finally, the biggest thank you to Dr. Shailene Tanimoto, who ran this whole week. Thank you, Shailene, for being amazing. Okay, only one small thing stands between everybody and food, which is that we need a picture of all of the students who participated in this lab. So we would like to ask all of the students and any instructors who are here. So any students, any instructors who are here, we're going right outside the front door of the building. We will take one short picture, and then we will come back. Parents, this is your opportunity to get through the food line before they descend on it. So I highly recommend using the next minute and a half to visit.
We will share the photos we take with everyone. So you can take photos on your own phone, but you don't have to because we'll share them.
Yep. Okay, thank you, everybody.
Thank you.